So once again, here's a depiction of the surface defined by this expression. Paraboloid, elliptical paraboloid, not a very good picture, but the surface between the graph of this and the plane z equals 1 lies above this region in the xy plane. And this region, of course, has a boundary that matches the boundary up here. And that boundary is the ellipse 0.04x squared plus 0.01y squared equals 1. And to set up the integral for the volume, we first of all, okay, I'm going to modify this. Can't read that word, but it's above the first quadrant. By the symmetry, if I want the volume of the whole paraboloid, I just multiply the volume in the first quadrant by 4 because it's going to be identical in every quadrant. Okay, well, let's look at this ellipse. Restricted to x greater than or equal to 0 or y, and y greater than or equal to 0. Okay, well, the ellipse comes up to y-intercept of 10, x-intercept of 5. And not very well drawn, but there it is in the first quadrant. Given x, the y-coordinates run from 0 up to whatever the y-coordinate is on this ellipse. So we're going to set this up. Now, this is one thing, and unfortunately WebAssign doesn't let me see your work. And let me just put in a plug. If your work doesn't show up, your work doesn't show up in WebAssign, if you can't get a problem and you're not getting a right answer, take a picture of your work and email it to me. I need to see what you're doing. Okay, and this is one of the big shortcomings of WebAssign. Doesn't show me, doesn't show the instructor how you're getting your results. And we got to supplement that, so please send me stuff. Okay, we're going to set this up by the inequalities 0 less than or equal to x less than or equal to 5. I don't know if you're using inequalities, I don't know if you're drawing pictures, but you should be. Okay, and then for every x, y goes from 0 up to whatever the intersection of this vertical line is with the ellipse. Okay, well, we know that 0.04x squared plus 0.0y squared equals 1. So if we solve that for y, we find the y-coordinate at which this vertical line intersects the curve of the ellipse. And now I'm messing up the arithmetic. I believe that's right, because if we subtract the 0.04x squared from both sides, we get 1 minus 0.04x squared. If we divide everything by 0.01. That's the same as multiplying by 100. And we're going to get 100 minus 4x squared. And maybe I ought to write the thing out because I was not gelling. I guess it's very simple. Okay, we have 100 minus 0.04x squared. We divide by 0.01, we get, and we got 1 minus 0.04. Divide by 0.01, we get 100 minus 4x squared. And I guess I don't want to factor out that 10. Trying to do two things at once. Okay, you can check my algebra on that, but it's pretty straightforward. So that when x equals 0, just to kind of check this out, if x is 0, you get the square root of 100. And if x is 5, you get 0. So when x is 0, y is the square root of 100, which is 10. If x is 5, y is 0. That agrees with the curve, and that has the right form, so that's going to be most likely correct. Okay, well, now we consider some increment here. Delta x by delta y, and you really want to do this. If you don't, you're just kind of shooting in the dark and hoping you get it right. With a sample point, x star, y star, and you ask yourself, okay, what do we find above this region that's relevant to what we're trying to find, which in this case is the volume. So, well, okay, this rectangle, well, let's just say this point here projects up to the surface. Got to find a tray. Okay, projects up to the surface at this point. So this is where we intersect the surface of this ellipsoid. It intersects here, and then it goes on up to the plane z equals 1, which is very clearly this plane. So it goes from here, and then it goes all the way up to here. And when you get up here, of course, you've still got your delta x by delta y. Down here, you have a sort of a curved section of the surface, which is hard to see from underneath, so take this with a grain of salt. And you have all the volume between here and here. It follows that you're looking at points that have z coordinate between, well, here's your function, 0.04x squared plus 0.01 y squared minus z equals 0. If you know the values of x and y, you can find the value of z corresponds to this. So z equals 0.04x squared plus 0.01 y squared. Okay, and if you're using the sample point, that would be your x star squared, your y star squared. So the coordinates of this point are these. So z goes from this coordinate up to the coordinate here, which is 1. And I can say then that within the volume, if your x and y are defined by these inequalities, then your z-coordinate runs from this coordinate to 1. So now we're going to write our integral. Okay, starting with the z limits, we go from 0.04x squared plus 0.01y squared to 1. Y goes from, didn't leave myself room to write all this, square root of 100 minus x squared. I did leave myself room. From 0 to the square root of 100 minus x squared. And then from 0 to 5. Okay, so x goes from 0 to 5. Y goes, for any given x, from 0 to the square root of 100 minus x squared. Z, for any sample x and y, goes from 0.04x squared plus 0.01y squared up to 1. That's what the picture tells you, that's what the analysis tells you, and that's what the integral is going to give us. Now I'm not going to go through the integration. Integration is pretty straightforward. In other words, when we do the integral with respect to z, we're going to get 1 minus this. And then we do the integral with respect to y. Well, okay, I'm going to just write it out. Said I wasn't going to, but I better do at least this much. Okay, so there's the result of integrating with respect to z. I'm not going to go through the details of that. And then we integrate with respect to y, and we're going to get y minus 0.04x squared y plus, I'm going to do y cubed over 300 evaluated between the square root of 100 minus x squared and 0 with respect to x. So we substitute square root of 100 minus x squared Okay, now factoring the y out of these, I get the square root of 100 minus x squared times this expression. minus the 3/2 power of the square root of 100 minus x squared over 300, and that has to be integrated with respect to x. You're going to use a u substitution. Let's say 10 cosine x. And I'm just going to put an etc. down there because I don't want to go through the details of that. It's a straightforward application of a trig substitution. You don't want to take the time to go through those integration details, which just comes back to basic first-year calculus. So if you don't know how to do this, well, I've advised you many times up to this point, yeah, you've got to review that integration technique. Now, one advantage of the course that I basically have can and could be copied to a 64 gigabyte SD card or some other device. I do go through all these details, okay? So if you need to see those details, that would be a good point of reference. And it's fairly easy to find what you need on that. Set of videos and narrative and stuff. Okay, so whatever you want to call it in that course. Now you can also find examples online, and that's equally good if you can find the examples that you want to find. So there it is. Now, next question is, what if we have a density on this thing? Okay, a density. Then what we can do is we can say, well, okay, between here and here, we're going to have some volume increment. It's going to be a rectangular type volume increment. Okay, here's our volume increment. So I'll kind of shade the front of it. And it's a little sloppy, but you can understand just a rectangular solid, rectangular region in here, rectangular parallelepiped with dimensions delta y by delta x by delta z. So if I pull this thing out, I can draw a bigger version of it. It's delta x by delta y by delta z, and it's going to contain a sample point x star, y star, z star. You have to have that picture to really understand this, otherwise you're just imitating symbols, and that usually doesn't lead to reliable learning. Okay. Now, if you confine your attention to this, you know what the volume of this is. It's delta x by delta y by delta z, which is why we get the dx, dy, dz here. That's your volume increment. Okay, this is a this is your delta V. It's that thing that shrunk to the limit where the delta x, delta y, delta z all approach zero. Now I can put those in any order. You know, it could be delta z, delta y, delta x. The order in which I put them just depends on how I describe my region. I choose to have fixed limit on x. I could have had fixed limits on y. I could have had fixed limits on z. I could have done it in any one of these ways. But having put the limits on x, I find my limits on y. Knowing my limits on x and y, I then express my limits on z within this region. And then I go back and think to this, and I went through the details of this, a lot of detail in the last class before the exam. Okay? We get this sort of thing. We get this specific region that we're going to focus on. Now within this region, if we have a function that tells us mass density, then what's the mass within this region? That's a question. So, we'll use this one. So if we have a mass density, delta of x, y, z, that's a lowercase delta, often used for mass density, but often used for other things as well. Then the mass within a typical delta x by delta y by delta z increment is, I'll say, the average density times the volume. I say average density because this density function can vary. Could be constant, but it could be variable. It doesn't matter. If you multiply the average density by the volume, you get the mass within the region. So I'm going to say delta M, the mass contribution of this region, is average density at x, y, z times the volume of that region. And that's approximately then equal to delta at x star, y star, z star times delta x, delta y, delta z. Okay, now the total mass is the sum of all this stuff. And I won't go into the rigor of that sum, although you need to do that. I did it once. You need to think through it and follow that sort of rigor if you want to really understand what's going on here. Just want to get the right answer with pretty good understanding. You see that this leads to the integral total mass is a triple sum over x, sum over y, and a sum over z. Of these contributions, and that's something that should be written out in detail. And that sum approaches through a process that shouldn't be all that mysterious. Triple integral for this region of delta of x, y, z, dz, dy, dx over the region which we've formally formerly specified as this integral with z limits 0.04 x squared plus 0.01 y squared. Limit here is 0, square root of 100 minus x squared, written pretty small, hard to read, and then 0 to 5 on the x. This works no matter what your density function is, because no matter what your density function is, the mass contribution of this little tiny increment is the density function, the average density of the density function over that increment times delta V, which is approximately equal to delta evaluated at your sample point within that tiny increment, multiplied by the volume of the increment. You sum that up, do the limit, you get the integral. Now in the limit, of course, the average density will become the density at the sample point, because everything shrinks to the sample point. And as long as the density function is continuous and well behaved, properties that we used to rigorously work out in this course, but which seem to have been shunted off to an analysis course sometime later, we get this integral. Okay? In the materials that I have sort of recommended, or at least that I'll make available, whether they're recommendable or not, we do go into more detail on those connections. So that's one example. Once you have this picture, you can do this. And once you have this picture, you can do anything else if you have the right not anything else. You can do a lot of other things if you have the right information. You can find the moment of inertia. You simply multiply the mass of the region by its distance from an axis of rotation or a point of rotation. That's easy to do. I'm probably going to go ahead and do that because that's coming up. Many other things, a lot of which come up in chapter 16. Okay, so we have to have this picture, and this is really the basis of understanding integration. You got to be able to describe the region with inequalities. You got to be able to think about what the typical increment contributes to whatever it is you're trying to find, whether it be volume, mass, moment of inertia, charge, whatever.